So yesterday I ran out of time in doing some explicit computations that I wanted to show you. So I guess I'll just pick up those ideas and then continue with what I had planned in a shorter version of what I had planned for today. I will have to squeeze a little bit the things, but I think might have enough time because the second part is I have prepared some slides, so that should be faster. Okay, so what I want to recall for you is the yoga, the logistics for obstruction theory, classical obstruction theory for sectioning as a map. So suppose in general, so suppose one has a vibration F, E, P, B. And the question is whether you can produce a section, a continuous section for this. So does it have a section S? So that's a map from B back to E, so that compose it with P, as P is the identity. Then in general, this is the situation. So what you want to do is assume that B is, to begin with, a CW complex. And the idea is to start trying to produce sections defined on the skeleton of this cellular structure and try to just stand one time at a time, one step at a time. So suppose, given we already know have a section defined on the skeleton BK. So what I have here then is BK, the skeleton. Of the cellular structure. So I have here the inclusion, and what I'm assuming is that I have this section. Well, I would like to ask if I can extend it to the next layer of cells. Okay, well, then the yoga of these things, I'll try to say a little bit more precisely what this means, is that you can produce, there is a cohomology class, CS. C is meant to represent a cocycle, depending on the partial lifting. And this is going to be a cohomology class. In the cohomology, K plus 1 of the base with coefficients in the homotopic groups of the fiber in dimension K. And one has to be a little bit careful here. This is a cohomology with twisted coefficients. Namely, the fundamental group here of B acts in the usual way on the fiber. Actually, in every homotopic class of maps of paths on B can be lifted to a homotopic class from maps from F into F. And then you can take cohomology or homotopy. In this case, I'm taking pi k of that thing. So one has to take that into account. And this is so that, well, the nice thing here is that this class, to begin with, it depends only on the homotopy type on the vertical homotopy type of the restriction of this, sorry, S is G, the section, of the restriction of the section to the previous skeleton. So this depends only, in principle depends on the section, but actually it depends only on the vertical homotopy type of S restricted to the previous skeleton. Now, let me just clarify what vertical means here. So, well, you could think of maps, two possible liftings being, and I said that I want to restrict it to the skeleton BK minus 1. So I have this composite. And you might wonder if you have another map which is homotopic, just in the usual sense, to this composite. Well, I'm going to require that this homotopy remains stationary when you project down to the base. So a homotopy between this thing and another possible such map would just be a map from BK minus 1 times 0, 1 into E, so that the initial branch is one of the maps and the final branch is the other one. But I also want that if I compose down to here, this is just, this is independent of the time, and it's just inclusion. In other words, you want to say that two maps are vertically homotopic if you have to perturb, you have to deform this map in such a way that if you keep fixed one point and you look at the time, this path happens only in the fiber where you're working on. So this has to be done vertically on fibers. The deformation has to be done without leaving the fibers. Of course, I need to assume that this is another lifting, so that this composite and this composite are the same here. So every point here is sent under this thing or on the other map to the same fiber. And then the deformation is point-wise is taken, it takes part in the fibers. Is it clear? Okay. So, well, it depends only on the vertical homotopy type of the restriction. And what is even nicer is that it is actually, you can think of this as an obstruction to being able to extend this partial section to the next skeleton. Namely, if there is no such obstruction, then, and if and only if, not quite that S can be extended to the next layer, but you can modify this lifting on the top cells so that then you're able to extend it. If and only if the restriction of S to BK minus 1 can be extends to a section for P over BK plus 1. All right, so this is actually very nice. So you have a little bit twisted but manageable model where to understand these obstructions and just to keep track of this process. In general, I'm not saying that it is easy to compute cohomology groups with twisted coefficients, and it's even harder to actually identify the obstruction in those groups. But there are some nice cases, usually the ones that one can manage, where for some reason you can show that these groups are 0, and then the obstructions have to be 0, and then there's simple enough obstructions just to keep on lifting things, perhaps modifying, so you have to extend, and you have to modify over the last layer, and so be able to extend once, and so on. Now, however, these things really depend on the previous and on the partial lifting. namely on the vertical homotopy type of its restrictions. So it's conceivable that you can find several such classes. In other words, if you start trying to sectioning over the skeleton a fibration, then, okay, maybe you're able to get up to certain layer of cells, and then you will say, oh, oops, I just computed a non-trivial obstruction. Then that doesn't mean that there is no global obstruction. It only means that you have to go back, modify your partial lifting, not only to the previous skeleton, but perhaps you have to modify it in smaller levels to be able to now keep on lifting. So what this means is that in general, these obstructions are not well defined. They do depend on the way that you are partially lifting. And this can be, so this list, the drawback is that, however, these classes in general are defined up to certain indeterminacy. So they really, if you want to take care of all of them at the same time, then, well, okay, you have to manage a set of such classes, and a way of doing that is by considering a well-defined element in these cohomology groups modulo some indeterminacy. But then this is a big problem in this process, dealing with indeterminacies. However, there are some good news. The first real obstruction that you will actually potentially find has trivial indeterminacy in the following sense. So suppose, yet the good news for this bad news is that suppose that all the homotopy groups of F are 0 up to, say, less than k, and say that the kth homotopy group is non-zero. So I'm just saying the fiber is k minus 1 connective. So there are no obstructions when the index, maybe I should use another letter, k, start, and the start is like that. So for as long as k is less than the start of the homotopy groups of the non-trivial homotopy groups of the fiber, well, even if they are not twisted. The groups here are trivial in that range, and so these classes have to be trivial, and therefore you can extend, modify until you get to that layer, until you get precisely to BS, essentially. So if this, then there are no obstructions to producing a section over the skeleton BS. So all the obstructions for that would lie in trivial groups. Now the good news is that, okay, take such a section. Say we have E, B, S, inclusion, and pick such a section. The good news is that you can do pretty much the same yoga to show that, okay, what's the obstruction for vertically deforming any one of these liftings into another one. There might be several such liftings. As you said, there is one, but there might be several such liftings. And if you start with one or you start with the other, you may, depending on your choice, you might get into a dead end, not being able to continue lifting. So which one is the best one? Well, it doesn't really matter the first time that you see this possibility, because all of them would produce obstruction, the same obstruction. Namely, there is an obstruction for vertically deforming one of these liftings on the first stage that is relevant to another lifting the restrictions over S minus 1, but those obstructions lie in groups that involve these groups, which are trivial. So essentially there are no obstructions for deforming any one such lifting into any other one, at least when you restrict to the previous one. And because of the first property, then the class does not depend on the chosen lifting. Say this. Then, same kind of ideas, assert that there is no obstruction. I've been just very vague, just saying the yoga. I can tell you a little bit more of the constructions if you want. There is no obstructions to vertically deform the restrictions to Bs minus 1 of any two such liftings. S as above. So there is a well-defined first obstruction. So definition, the fundamental class for sectioning P to Bs plus 1 over on, to find in a section on this guy, is a well-defined class in the cohomology S plus 1. Start with any section, then you have associated this obstruction. It doesn't depend for what I said on the chosen section, and that's the obstruction for finding the section on the next layer. So this is an element in the cohomology of V with coefficients on PS, the first really non-trivial homotopic groups, and maybe you have to take into account this twisting. So let me call it just eta P. That's the real first obstruction for getting this section. Okay, so here's an example maybe. So suppose you have a vector bundle, X, alpha over X, and well, just consider, so let me just be more precise perhaps. Take a manifold and take the tangent bundle. That is explicit. So I want to define the Euler class. And the Euler class is just the first obstruction for finding a nowhere trivial section for this bundle. In other words, well, I want non-trivial, nowhere zero section, so let me just take this sphere bundle. And then the fiber, say this is of dimension n, so the fiber is the sphere n minus 1. That starts in dimension n minus 1, and so you have the first, the fundamental class in here lies in the cohomology of n, which is the next number where the homotopic groups of the fibers start, which is n, m, with coefficients in Z. Usually, well, if the manifold is oriented, then the system of coefficients is trivial, and you get just usual cohomology, and you get the Euler class. So in this case, this thing is nothing but the Euler class of the manifold. It's really the first obstruction. And notice that it is also the last obstruction. It's the unique obstruction, because next obstructions would have to lie in higher dimensions, and this is of dimension m, so you would not see anything. Even when there would be homotopic groups in here. So, well, that's But you can do this even for non-orientable manifolds. But you have a twisted Euler class. Good. So this is more or less how this thing works. Now, let's go back to the example that I want to work out in detail for you, this situation for computing topological complexity of configuration spaces. So let me recall some of the things that I noted then here. So recall, I explained how knowing the cohomology of these configuration spaces, let me call this space, just to save time, configurations of dimension m and endpoints, just to save time. These are endpoints in Euclidean space of dimension m, point-wise different, pairwise different. So, well, recall that the cohomology of these things with any coefficient is generated, say with integral coefficients, is generated by classes I, A, I, J, so that J is less than I, and they are in this range, and they satisfy a nice relation that I always forget, but I wrote yesterday. And in particular, this it means that the homotopy dimension of these guys, M, N, you can find a cellular complex with the homotopy type of that, which has cells in between n minus 1 and n minus 1 times n minus 1. So this is, well, the top cell lies in dimension n minus 1, the bottom cell that lies in this dimension, the F n m is n minus 2 connected. So it really starts in dimension n minus 1. And using this, and just comparing with the case where you can't passively find any obstruction, we saw that the topological complexity of this guy is bounded from above by 2n minus 1. That just comes bidimensional divided by connectivity reasons. And then there is let me be a little bit more precise on that thing. So an exercise, given the explicit structure that I just mentioned for the cohomology of these spaces, well, you can take a look at the algebra of zero divisors, and the exercise is to show that the product, there is an explicit product of elements of the following form. These are zero divisors, cohomology classes in the Cartesian product. You have to square them, and this is non-zero. This is non-zero if M is odd. This is just a explicit, a little bit straightforward computation. Now, notice that there are n minus 1 factors, but each one of them is repeated 2. So there are two n minus 1 factors. And all of them are zero divisors. So 2n minus 2, the number of factors, is a lower bound for the topological complexity, as I explained in previous things. And so you get that this is actually an equality in the case where n is odd. So, and thus a topological complexity in that case for m odd of this guy is 2n minus 2. So what happens? Let me describe what happens for m even. Notice that for m even, Well, these cohomology classes, I said yesterday, the degree of these guys is they are spherical. And they come from a sphere of dimension n minus 1. So if m is even, right? If m is even, so that the dimension of these classes is odd, this means that the square is 0, because of anti-commutativity. So it is obvious that this product is 0, just because each factor is 0. So it's not going to work. So the second exercise has two parts. The second is a bit tricky, but it says that, well, you can find a replacement for that product in the following form. So another exercise is if m is even, then the following product 2. Notice that I have to go from 2 because that number has to be just larger than 1. And I'm using all possibilities except that I just need 1 here. I could use any other index there, but it doesn't really matter. But now I need to use other indices. So I take AI1 tensor 1 minus 1 tensor AI1. I don't square them because I would get something trivial, but I can then multiply by up to n by using some other index, and say I use 2. Okay, this time I get as many factors but 1 less, because I'm missing 1 here. So here there are, well, the thing is that this is non-zero, of course. So the topological complexity of that guy in this case is at least the number of factors here. And the number of factors there, so that's the end of the exercise. Thus the number of factors, which is 2n minus 3, is less than or equal to the topological complexity of this guy, which is, by the way, just 1 below the upper bound. So we have to really decide what this value is, and it turns out it is, the value is this. So in fact, this is an equality. So, and you do have to analyze a first obstruction. Well, so let me count how many obstructions do I have? Well, you have to actually understand some of the yoga of the obstruction theory. So let me just count how many obstructions do I have. Should be clear, or at least intuitively clear, that since this is the number that you get by just not having any section to deal with, if you want to have that this is also an upper bound, there should be only 1 obstruction showing up. So let me just be more precise. That would be cool, because if there is only 1 obstruction, that would have to be the fundamental class. And that has 0 indeterminacy and can be computed in cohomological terms, still in cohomological terms. Okay, so how many obstructions? So what are the obstructions for having TC of this guy at most 2n minus 3? This is, of course, the sectional category of the evaluation map being not greater than that. And recall, so this is the sectional category, CCAT. Notice that this is lowercase letters, so it's not last name. Okay, so this is CCAT of the double evaluation map for associated to this space. And recall that, in other words, what I explained yesterday is that this multiple sectioning problem can be translated into a single sectioning problem for a different vibration. So Having this less than that is the same as having that the join of that many copies of this evaluation map is 0, that it has a section. So I have just passed the problem to replace the vibration by another one where I only need to care about finding a section. So what are the obstructions in terms of obstruction theory? Well, let me just draw here the vibration that I'm working with. So the vibration is, the base space is this configuration space. I've been denoting by FMN, and let me also denote it just by F, just N and M are fixed here. M, by the way, is even. So you have the same base, but now I have 2n minus 3 joint power of this evaluation map via the map that I put there, 2n minus 3 E2. So recall the definition of this is that this is a iterated power, fiber-wise joint power of the evaluation map with itself. The evaluation map, double evaluation map, has fiber, of course, loops on F, and so this has fiber, an iterated joint, usual joint product of the fiber with itself with as many as 2n minus 2 copies. Recall my normalization notation. And I want to produce, understand the obstructions for producing such a section. Well, how connective? We know what is the dimension of this guy. This has dimension, the base has dimension 2, n minus 1, n minus 1, because each piece, each factor has dimension half of that. Now, where does this start? Where does the homotopy groups of this joint product start? Well, recall, so here's a very useful fact about joints, that the joint has the homotopy type of the suspension of the smash. So, fact. Well, you don't really need the parentheses. So, if one factor, say, starts in dimension A, the other factor starts in dimension B, and the whole thing starts in dimension A plus B plus 1. All right, so this starts, this single guy starts in dimension n minus 2, I guess. How connective is this? N minus 2. So F starts in dimension n minus 1, which is the dimension of the generators A. So the loop starts in dimension n minus 2. Now, of course, if I iterate this more, this just says that this is going to be the smash product with one less suspension than the number of factors. So this really starts in dimension, the whole thing starts in dimension n minus 2, which is where each factor starts, but you have as many as 2n minus 1, and then you have to add, let me see if I'm counting correctly. Right. And then you have to add the number of suspensions. The number of suspension is 2n minus 3. For instance, when you have two factors, this has the homotopy type of X. The number of factors, you have to add one suspension. So if you have here 2n minus 2 factors, you have to add 2n minus 3 suspensions. So that's the start. And well, you do a little bit of algebra. What this is 2n minus 1 times n minus 1 minus 1. If I did not make any mistake, I minus 2. I think that's what you get, 2n minus 2. Right, that's right. That's what you get after doing this thing. Okay, so obstructions for this sectioning problem lie in the cohomology. Well, let me just say a little bit more explicit here. So that is the situation that I have to consider. And the obstructions, with obstructions in the cohomology groups of the base with coefficients on that thing, the loops on F, joined with itself as many as 2n minus 2 times, twisted. Now, what are the conditions for these groups to be trivial? Which are trivial if, well, let's see, one condition would be that this number is greater than or equal to the dimension of this space. You would not be seeing any cells to measure homology. So if either j plus 1 is greater than the dimension of that, which is 2n minus 1, n minus 1, or the other situation would be that this system of coefficients is a system of trivial groups. So if j is less than the dimension, homotopy dimension where this fiber starts, or if j is less than, and I just computed that, if j is less than that. J being less than that, it just means that j plus 1 is less than 2, n minus 1, n minus 1. Right, so I didn't make any mistakes. So as long as j is different from this number, there's just no obstructions. And in this case, there is one single obstruction, really the first one, and really the last one. There is only one obstruction. But the question is, okay, I still have to say how to deal with this obstruction. So the only relevant obstruction is that. Well, now let me give you one further, perhaps not so well-known property of these obstructions classes. At least it wasn't for me. And so let me just give you the result. Turns out that the fundamental, so suppose you have your fibration, and the fiber starts in some dimension, and you take the fundamental class, right? Now, suppose that this fibration, you multiply it with itself, fiber-wise, joined in a joint way and fiber-wise way with itself so many times. What can you say about the fundamental class of the resulting fibration? It has to be the answer, which is very nice, is almost a power of the fundamental class of the original vibration. So this is the result. It's an old result of Schwarz. Well, I guess it's the Schwarz. It's the first time that I've seen it. This goes back to the late 50s, I guess. And maybe Stingrod knew it by the 80s or so. I don't know who it's, but this is standard. It says the following. Where am I? Lost it, but I had to just tell you from the back of my mind. Let me see, suppose as usual, you have this vibration. One thing that I didn't say is that, well, you need, I said so. The fundamental group of this has to act, you need simplicity of the homotopic groups of here so that you really have an action, well-defined action. You have to deal with base points. Anyway, so suppose you have this vibration, and suppose that you already have, with some reason or other, you already have a lifting up to certain level with a section over BK. All right. So say, so we have already a section I have E, B, BK included here. I have this section. And let me say that with a obstruction class given explicitly by some eta. Let me call it eta P. With obstruction class in the cohomology of K plus 1 of B pi K of the fiber. All right, so it has associated some obstruction if you need to extend it one further layer. All right, now what can I do? Now, let me consider JLP, which goes from JLP into B. So I'm just taking the original vibration, multiplying it fiber-wise, in a joint way, with itself as many as L plus 1 times. So I know the fiber is a usual joint product. And then this guy admits has a section over B K plus 1 L plus 1 minus 1 over this skeleton. There is a section. Just for free, you can just take a sort of a joint product of this section with itself as many times, and you are in good shape to produce a section on this skeleton. Okay, now what's the obstruction? So you get for free a section, a much higher section for this joint product. But what's the obstruction? Well, the point is that has a section on here with obstruction class. The obstruction class would lie in the cohomology of K plus 1 times L plus 1 of the base with coefficients on the homotopy groups. K plus 1, L plus 1, minus 1 of the homotopy groups of that vibration. Now, what are the homotopy groups of that? It's just the joint product. F joined L plus 1 times. Well, but that's not it. You don't only get this, so let me call it, eta P J L P. But these two, the thing is that these two guys relate to each other. Notice that I could take the nth power of this guy, and I want to say that it essentially maps into here. And, well, the way that, so this is so that. Let's see. I have a map. Consider eta P to the L plus 1 that lies in the cohomology of K plus 1, L plus 1. So I'm taking just the L plus 1 cut product of this thing with itself. That lies in the cohomology of B with coefficients in the homotopy groups of F tensor L plus 1 times. But now, notice that there is a map. So the condition, I'm just stating the result. The condition is that this guy consider this map that goes into the cohomology of K plus 1, L plus 1 of B, finally with coefficients of this guy. This is a star. That, I haven't said what this map is. I'm going to do it. But in such a way that this class maps into this class JL of P. So you do have some sort of control on the obstruction theory, on the obstruction class for the next lifting of this free section, of this free section. You have control on that as long as you have a reasonable control on this power. And this should sound to you like I need to prove that this is going to be a zero divisor, and if I know that zero divisors of so many zero divisors are zero, then I would only know that this is trivial, and I would be in good shape. But let me be more specific. So I need to say what this map is. So I need a map from here to here, and this is just the joint map. Namely, notice that you have the joint map that goes here. The map is just the joint product in homotopy groups. Namely, if you have an element in the homotopy groups of a space, and you have another in the homotopy groups of another space, then I claim that you have obviously a map into the joint, into the homotopy groups, one further dimension in the joint. And this is just taking joints. Joint construction is functorial. So if you have a map is A into X and a map is B into Y, just take the joint of them, which goes, the joint of two spheres is the sphere of dimension 1 plus the sum of the dimensions, and that goes and lands into the joint product. And if you do just the counting, you precisely arrive from here, and you iterate it, and you arrive precisely here. All right, so let me apply that situation to the case of configuration spaces. And well, I need a third exercise. This is the tricky part. This is really the second part of the exercise number 2, which I just gave the first part. So I just said, I gave this explicit product. Recall that there was something like this. Some explicit guy being non-trivial. This has length 2n minus 3. This was part A of the previous exercise. Part B that I should have mentioned is that any product of zero divisors, whatsoever they are, which has one more factor, has to be trivial. However, any product of zero divisors of length 2n minus 2 or higher vanishes. In principle, you can prove this just by straightforward computation because you do know the cohomology of the configuration space, therefore the cohomology of the Cartesian product, therefore, and you know the multiplication structure, so you know what the zero divisors are, and you just do a full search somehow. But you can do this in a little bit more tricky way, indirect way. But in principle, this is doable if you want to try it just by computing. Okay, so let me use this result to the case that I'm interested in. Okay, so let me find it. That. Sorry, I had to rearrange. Here it is. Oh, this is the theorem, and then here it is. Okay, so what numbers should I take in that situation? So recall I'm working with F, the configuration space of Rm with n points, and then let me take in this result that I already erased, K to be m minus 1. K, what was K? K was the lifting of P in the skeleton of dimension K. So here, of course, P is going to be the evaluation map. I am in that vibration. K is n minus 1, which is the first homotopic group of the space, of the base space. And let me take, so that's K, and L, let me take L to be 2n minus 3. Because that's precisely the, recall that the vibrations that I had in mind were, let me be more specific. So I have F times F, F01, E2, that's P, loops of F. But then I don't want that one, I want J2n minus 3, E2, into J2n minus 3 of that thing, with fiber, some iterated joint product. Loops F, loops F, join into n minus 2. So that's the L. That's the L in the result that, unfortunately, I erased. That's here. That's the L. 2n minus 3. So now, I need a section. On the skeleton of dimension n minus 1. So need a section from F cross F into, well, it is dimension n minus 1 here, F cross F, dimension n minus 1. I need this lifting to apply this result. Well, that's for free, because what are the obstructions for finding these guys? The obstructions for getting into here involve homotopic groups of the fiber in dimension less than n minus 1, and that this fiber is so connected. Actually, that's where these, the homotopic groups of this fiber start. So you really have this one, this section, for free, just because there are no obstructions. And in fact, the cohomology class is just the fundamental class of that vibration. That's the obstruction. Okay, but now I, for free, have a lifting of this other vibration to the skeleton, F cross F. And now I have to go to M, guess, K plus 1, M plus 1. I have a lifting, this lifting, M times, I hope I'm not going to do a mistake here, 1 plus L, which is 2n minus 2, minus 1. So I have this skeleton here, and I have a lifting. Now, if I did the counting correctly, this guy, this is the top dimension of this space. So this is actually an equality. Let me not go into the checking that. I hope I didn't make any mistake, but that should be the whole thing. That's just the top thing. And you have, sorry, one less than the dimension. Sorry, let me correct. This is just one less of the dimension. This is you have to remove the top cells, the really high top cells. And I have this for free, and I would like to be able to extend it to the last layer of cells. All right? And that would be it. And there is an obstruction, and the obstruction is, by the result, comes from a power of, this obstruction comes from a power, the L plus 1 power of the fundamental class that I have here. Okay? So I have this for free. And it has, sorry for the organization. But the point is that this has obstruction class, an image because of this Schwarz's theorem, an image of the original E2 fundamental class to the power L plus 1, which is 2n minus 2. 2n minus 2. So that's the obstruction. It's some image under a change of coefficients given by multiplication in fundamental groups by the joint product. But it comes by from this class. Okay, now the key point, is that, okay, I wrote here part 2 of an example that said that any product of zero divisors, suppose this is a zero divisor, of this length has to vanish. Because I remember that I had a product of 2n minus 3 products, factors of zero divisors, and that gave me the lower bound 2n minus 3. But now I have here a product of length 2n minus 2 of this guy. So punchline is that if I can show that this guy that lies in the cohomology of here, and is the obstruction for this, lifting this one more stage. If I can show that this class is a zero divisor, then I will be done, because it's a product, a large product of zero divisors. That would be trivial, and so there is no obstruction for lifting, extending this guy, perhaps modifying a little bit on the top cells here, and then extend it one more layer, and then you would get the whole thing, and you would get your section, and we would be done. So punchline is that this fundamental class of E2 is a zero divisor. And this is very naive, of course. This is the easy part. Namely, okay, so that's the fundamental class of the original double evaluation. So what's that? That's F times F, E2, and then I have here that thing. And I want to show, I have here this fundamental class, the first one. So I want to show that it is a zero divisor. Namely, if you take the diagonal, that should map trivially. I want to show that that goes to 0 here. Well, the point is that it does just for free, because notice, the image here, this is the fundamental class, here, should go by naturality of the fundamental class, because it is well defined, it has no indeterminacy, should go into the fundamental class of the restricted vibration. So take delta, pull back under this, and you have some pullbacks thing with the same fiber. And what I'm trying to say is that I claim that this vibration is trivial. In other words, that you have a lifting here. But that is obvious, because notice, what you could do is just observe that a homotopic replacement of this vibration is given by this covibration. Or in other words, if you want to just be more down to earth, take the map from F into the path that just takes a point and sends it to the constant path at that point. So you have this map. If you evaluate it, that was a constant map, and so you get into the diagonal of this point. So you have this lifting, and therefore this vibration, when you pull it back into here, is trivial. And therefore there are no obstructions for lifting. And so the first obstruction, the fundamental class, has to be 0. So no obstructions, and we're done. Okay, so let's, sorry. Well, I hope I didn't go too much into details. What I want to do now is present you some work in progress also, where I take a little bit modified version of obstruction theory based on Hough invariance for approaching this problem in a slightly different way, but which is better suited for analyzing topological complexity of other simpler spaces. The motivation here is the following. We know what the topological complexity of a sphere. This was very simple. This is either 1 or 2, depending on the parity of n, if this is odd and this is even. So let me give you, the goal now is to give you an explanation of this fact. This is very easy. It uses only cohomology. But I want to give you a homotopy explanation. Actually, I want to connect this phenomenon with the fact that the Hopf invariant of the y-hat square of the identity on a sphere is either 0 or 2, depending on the dimension of the sphere. So I'm going to be defining some of these things for the moment. So let me just motivate the whole thing by recalling some usual properties of, okay, no, I'm not going to use this, of the Ganea conjecture. The Ganea conjecture is a statement about what happens when you compute a question? No? The category of a product of spaces, and is a property of that is that the category is subadditive in the sense that it is at most given by the sum of the categories of the factors. Question is, can this be an equality? Usually not, and it's easy to produce examples of spaces where this is not an equality, and essentially it has to do with torsion. If you produce here a Moore space, two Moore spaces with different torsions, then this would not be an equality. However, Ganea conjecture, okay, let's put a very simple space, a sphere, that has no torsion and is one of the simplest, homologically speaking, spaces. Now, Ganea conjecture that was always an equality. Tudor Ganea, I guess. And just at the beginning of this century, Norio Iwase showed that that was false, but you have to do really very hard unstable homotopy theory to understand, just to produce an explicit control example. So, well, now it turns out that there is a similar thing if you replace cat by TC. However, you would have to use here TZ of a sphere, which is sometimes 1, sometimes 2. And so the problem would be at least that. So it's at least it's a bit more complicated. Okay. So what we can... Now, more generally, it is quite clear that if you have... Let me consider the problem to what happens to the category of a space when you attach a cell. Well, it's easy to see that if you are attaching a cell to a space, essentially you are putting one extra contractible space if you just take a little bit above this cell. So here's the space to which you are attaching, and here you have the cell. This is already being divided into pieces, open pieces, which are contractible. And then you're attaching this extra cell. Now, each one of these pieces can be extended. So take the attaching map and take the inverse image of this thing. So this goes and attaches over here. Take the inverse image of that. That corresponds to a little bit of this. You can extend it a little bit as a cylinder. And you produce a slightly extended version of this open set, but now here, which has the same homotopy type. It's contractible. And then you have 4 here and one extra one, which can also be contracted to a point. So the category increases at most by 1. Now, the question is, what happens to the topological complexity of a space if you attach a cell? Well, it can go up by 2. For instance, topological complexity of the projective plane is 3, but if you remove the top cell, it goes down by 2. And this phenomenon is even, you would say this is the worst that you can have because this number. No. Actually, there are projective spaces, and this uses the relation that I explained in one of the lectures, that the topological complexity of real projective spaces is just the immersion dimension of these guys. And there are simple cases whose topological complexity you can actually compute, the immersion dimension, But if you remove the top cell, it goes down by as many units as you want. So this is kind of a more interesting problem. And well, I just meant to say here that this is related to the Hopf invariant one problem, because recall that this is an equality holding for non-parallelizable manifolds, namely for M except for being 1, 3, or 7. So let me just try to see what is going on here. Okay, so here's a definition of a relative. Let me go back to the robotics situation. Here's a definition of a relative motion planning problem. Namely, in the original version, you had your evaluation map, and you wander for sections which are continuous in some parts. But now, suppose I don't care about planning the motion from any initial state to any final state, but only in some actual tasks for the robot. Maybe the robot could be parked in some area, you don't know where exactly, but in this area, and it has to go to some other area. So in that case, A would be just as a product of subspaces of X. So just want to plan the motion there. So I wonder about sections which are continuous piecewise, and how many such pieces you need. So that defines the relative topological complexity of X. This is really being introduced by Michael Farber also. Of X relative to A, which is nothing but the sectional category of this vibration, but pulled back over A. Now, here's a basic question. What can you say about the topological complexity of a space if you know a little bit about, well, if you know the relative topological complexity with respect to some space A, and the way and the topology this space is inside X times X. And the thing is that you can actually, it's quite easy to prove the first part of this, which says, okay, more generally, suppose that you have two nested spaces, A and A prime, inside the task space of the robot. Then, and assume that A is obtained from A prime by attaching a cone on anything. It could be a cell, but just by attaching a cone on anything. Okay. This via is attached along a map alpha. This is an S. It's not supposed to be a sphere, just any space. Then it's quite easy to see that the topological complexity relative to the larger space is no less than the one relative to the smaller space. But actually they differ at most by 1. And furthermore, they are actually equal if and only if certain set of homotopic classes, which I will refer to as the Hopf set, trivializes. So let me tell you what this means. So as usual, as in these things, let me explain what this is. So in order to understand this, I have to be a little bit more general. So suppose you have any old vibration, a map from a space into B, and you want to understand the sectional category of this relative to phi. In other words, the sectional category of the pullback. And suppose that you have this cofiber sequence, namely, this guy has been obtained from this guy by attaching some cone. Okay, then under those conditions, it's easy to show, and here's the proof, that the relative sectional category is different at most by 1, just as in the previous slide. And here's the answer. So suppose that this is a picture of X. On the bottom is Y, and you've attached a cone on some space along this map alpha. And suppose you have these pieces of the base space of X, namely the base space of the pullback, in which, on each of which you have a section, a local section. Well, then you can do the same thing over here. You can just fatten it up a little bit. They have each one of these pieces fattens a little bit up to the same homotopy type. And then if you already had a section over here, then you have a section over here and here because they have the same homotopy type. And you're pulling back a vibration. So you recovered just the same number of local domains. And the only thing that you're missing to cover is a contractible space. And there you have a section. So they can differ at most by 1 anyway because of that. But of course, the important thing is to decide whether they stay the same or they do increase. And this is where the offsets come in. So let me just recall some of the conditions that I talked about in previous lectures. Namely, suppose that you have this vibration as usual. Now you can take over the n plus 1 Cartesian power of B a product of your original vibration with a bunch of identities. That goes from this product, many copies of B, one single copy of E, mapping down into here, and let me just call that Pi, where I is the factor coordinate where you put in the P. And you can just, all these are maps on this guy, and let me just take the fiber-wise join of all these guys. And let me denote it by that, and I will refer this as being a relative fat wedge. So how many minutes do I have? Five or so. Right. So, all right. Now notice that each one of these vibrations is obviously pulls back under the diagonal to P itself. So the fiber-wise joint product pulls back into the corresponding fiber-wise power of P. So that's, you have this pullback diagram. And of course, I already mentioned that this guy has a section if and only if the sectional category of P is at most n. And now you can relativize that to not only having a section for that, but maybe a lifting. So suppose you have this map. So if you relativize, it's easy to relativize that thing, and you would get that the relative sectional category of P with respect to this map is at most n, if and only if this map can be lifted through this relative fat wedge. Now, well, this is good. This is an if and only if situation. That's good because then that tells you that you can actually have a way of controlling what happens if this is small, whether this can have a chance of increasing. So now, for practical purposes, I want to replace, the previous vibration, this iterated fat wedge, by a covibration. And it turns out that you can do so. Well, of course you can always do that, but you can do it in a controlled way. Namely, you can replace from the beginning your vibration by a covibration. And then you get, so suppose you did that, you have an actual covibration, an inclusion map, nice behaved. And now you can take the following subspace of this base space. Namely, it consists of all these tuples so that at least one factor lies in the smaller space. So for instance, if E is a point, you get the usual fat wedge a la Whitehead. All right, so the point here, you have to prove that this inclusion is a cofiber replacement for the previous Whitehead, what I defined the Whitehead fat wedge, the relative fat wedge. But that's so, and therefore you get the previous result just tells you that the relative sectional category of a cofibration or anything that has the homotopy of this is a homotopy invariant of P, is at most n if and only if this map can be deformed into this smaller space. Well, that leads me to that definition. Namely, okay, so let me define the offset for this guy. So the basic assumption is that the relative sectional category of P over the smaller space Y is bounded from above by n. So by definition, that means that you have this lifting into this relative fat wedge. Okay, so you have this commutative diagram up to homotopy. And now I can compose this pair of maps. Notice that these both are inclusions. So I can compare this map of pairs with the map of pairs coming from the characteristic map. Namely, recall that I'm assuming that this is a cofiber sequence, so here you have a push-out diagram, and you have the characteristic map, and now I want to take the composition. So for any such lifting, that defines for you a homotopy class in there. You have to be a little bit careful because this is only commutative up to homotopy, but that doesn't really matter. And the set that you get that way is defined to be the offset. And then, Well, this is a standard in homotopy theory that, okay, this set is trivial. I want to say what that means, if and only if the sectional category did not increase. So this set contains all the information. And by this, I only mean that one of these elements in the Hopf set is homotopic to a map from here to here relative to S, so that you can use that homotopy to extend this previous lifting to a lifting in there. This is almost tautological in homotopic theory. Okay, so that's good. Now, I wanted to compare here, but let me just go to the case of topological complexity. 2 more minutes. Good. So let me put this to work on the framework of TC, robotics. So what can you do? Well, here you have this vibration. I already explained over here in this proof that it has the homotopy type of the diagonal. Nice. And I have these Hopf sets that depend on the lifting, alpha. So I'm going to be using this notation. This is the TC Hopf set for some preliminary lifting. All right. Now, you do have some homological input, but this is my final slide. Recall that the topological complexity of the sphere is either 1 or 2. And this is just a naive computation. But let me relate this to saying something more concrete about a phenomenon in homotopy theory. Well, so suppose you want to understand the sectional category of that, namely the topological complexity of that, of the sphere. I have this cofiber sequence. Here you have the top cell, the attaching map for the top cell in the Cartesian product, and well, suppose I want to understand the relative sectional category of that over here. Because this is a suspension. In one of the previous slides I explained that the relative sectional category here has to be 1. So suppose that's clear, has to be 1. So when you attach this cone, this goes sometimes up by 1 and sometimes stays the same because the topological complexity of that guy was either 1 or 2. So that means that the associated Hopf set is sometimes 0 and sometimes it's non-zero. Okay, but that depends on really knowing that the topological complexity of that behaves like that. But what about if I really want to compute this Hopf set and it turns out to be a single element? Well, the reason for that, and I'm going to finish with this, although I had an explanation, is that, okay, that Hopf set agrees up to a sign with the classical Hopf invariant of the Whitehead product of the identity. And it's well known that that guy is either 0 or 2, depending on the parity. So you do, for instance, in this case, you do get a trivial Hopf invariant, and so the thing stays being the same thing, and you can recover that guy. Or you get not only a non-trivial Hopf invariant, but you know that this guy is an integer, and you know that it is 2. And it's non-trivial, and therefore the thing has to go up to that thing. So this is kind of a framework to study more generally topological complexity of any spaces, or even more generally sectional category, for that matter, of any vibration, by understanding the base space through a sequence of cones, a cone decomposition of the base, and understanding the corresponding Hopf sets. And well, just let me mention that it is very interesting to note that the topological complexity, to note that the topological complexity of a space is kind of related to the category of the cone of the diagonal of that space. So take X, inside X times X, collapse a point the diagonal, take the cone, and look at the category. And there are many cases where these two numbers are the same. For instance, for spheres, because we know there is a very explicit model for this, is kind of neat understanding. This is a two-cell complex. And so this explanation, this homotopy explanation, can actually be extended to give a homotopy explanation of that situation. And more generally, there are some other spaces whose topological complexity is known, And the category of the diagonal, of the cone of the diagonal may be known, but they are equal. Interesting such situations are given by, if you allow me just to switch slides, and still one more minute, one more slide. Here, there are some more examples where this equality between TC of a space and the category of the cone of the diagonal agree, and these are kind of very interesting examples. At least in two of them I know how to explain this homotopically. But here is a very interesting situation. So suppose consider the Blackers-Massey element, the one that attached the second cell to sp2. And consider the cone, a very concrete two-cell complex. What can you say about the topological complexity of this guy and how it relates to the category of the cone of the diagonal? And there is a lot of interesting work to do here, some partial results, but well, just wanted to show you these sort of ideas because you can still be using homotopy theory to try to understand things that somehow are motivated by robotics.